Oh, hey there. My name is Fergus Casey. I'm a director of R&D in the ARC Processor IP team in Synopsys, mostly based in Mountain View. Today I'm presenting from my home office here in Danville, California. Over the next 30 minutes or so, I want to give you an overview of what it means to build a safe and secure SoC architecture for next generation automotive chips, whether it's semi-autonomous ADAS through to autonomous vehicles. Before I get going, I just want to um, raise the point that if anybody has any questions during the session, feel free to type it into your chat box window at any point in time. I'll look to respond to as many questions I can at the end of the session within the time allowed. So let's look at the agenda. Autonomous vehicles, I'll give you a quick snapshot progress report to date, where we were then, where we are now. Then we'll take a closer look into performance requirements for today's ADAS designs, explore some of the existing technical challenges to be solved, with a particular underlining around the safety as a cornerstone, where the success of next generation automotive semi-autonomous will really depend upon how good we can build our systems, the reliability of those systems from a safety perspective, but also from a security perspective. Then we'll deep dive a little bit into the SoC architecture for such designs, with a particular focus on building designs that are safe and secure. Then a little bit of a snapshot into the road ahead, some of the challenges that remain. So when we think about autonomous vehicles, we probably think about Tesla. We think about Waymo and others who have been investigating this for quite some time. But really, the dream started 70 or so years ago. We've been chasing that dream for quite some time. This is a picture from the 50s. Two couples enjoying a good game of Scrabble while they're being driven down the freeway. Things got a little bit more real in the 60s, where, as the writer of a particular article at the time relating to the automation of individual machines wrote that there's an extremely large number of possible systems, no more than 1,296. Well, since then and now, I think we could probably add a couple of zeros to that number. Roll on the 80s with Knight Rider. Things got a little bit more real again in 2010. Google started to invest quite heavily, as did the likes of Tesla, with respect to autonomous vehicles and automation. 2015, really nice concept cars from Mercedes, some funky concept cars from Google. Things got a little bit more real as we moved from 2017 and through to 2020. But the question is, are we closer now to achieving that goal than where we were in the 60s, 70s, and 80s? Before we look at progress and some of the technology challenges that we face, let's take a short look at the definition of driverless vehicles, divided into 6 categories, 6 levels. Level 0 being absolutely no automation or assistance whatsoever. Level 5 being the highest level of automation, where basically no steering wheel, the system is in full control. The reality is that the industry has been and probably will be for some time in level 2 and level 3 through adaptive cruise control type functionalities, active lane assist, active lane guidance, active braking, all of which are systems that are assisting the driver be a better driver on the road. Most certainly the buzz is around level 4 and level 5, but it's worth noting that level 2 and level 3 is also where the majority of key semiconductor players are today, either based on their current products or indeed looking at their 5-year roadmap plan. And that's pretty much where Synopsys see the focus over the coming 5 or so years. So looking at the case for autonomous driving, other than having a good game of Scrabble driving down the freeway, there's some pretty important reasons why autonomous driving is important, or even semi-autonomous driving is important. Let's take a quick look at the stats. roughly 30,000 people per year die on the roads in the US, and 92% are caused due to bad drivers. 8%, only 8%, are due to technology. So today's standard car on the road, that's still a very high percentage of fatalities due to human error. So in our industry and for our generation as engineers, our goal should really be and needs to be to reduce the fatality count, providing better driver assist mechanisms to avoid these accidents. Certainly our success will depend on our ability to reduce those fatalities. Likely, if we're able to reduce it by 5% or 10%, that's a major achievement. And let's strive to reduce the technology failures from 8% to potentially 0. So let's look at one of the key challenges on the road to autonomous vehicles. All pedestrians are not equal. We have fantastic AI algorithms to detect objects, to track objects, and a little bit more about that later. But there is no algorithm to calculate pedestrian behavior. Detection and recognition is good, but it will not be enough to recognize that a pedestrian is distracted while driving or walking across the road, or that a child at the side of the road is actually in a safe state, let's put it that way, because he is surrounded by his parents. So let's take a look at some of those AI technologies that exist today, the problems that we have solved. Step 1, object detection. Object detection is usually solved through FASTA or CNN and ResNet type graphs. Then once we have detected the object, we're now looking to track that object. So for this instance, we're using feed-forward neural networks, or RNNs, sequence-to-sequence learning, where you're predicting the next frame sequence based on historical information. Then step 3, more of a sensor fusion, where you're bringing those objects together on a single neural network engine to make decisions and determinations as to what is likely to be the next event. All good, and indeed in the early days of computer vision, the focus was very much on that object detection and people or cat detection. But an object needs to be understood within the context, as referenced in some of the previous slides. Considering your foreground object segmentation, your background scene, the combination of both of those together in a single neural network is what will allow your AI engine to fully interpret and understand the conditions and potentially any hazards that are about to transpire as the car is driving down the street. Panoptic segmentation. Here, the goal is to detect each object and delineate it with a bounding box or segmentation mask. Basically, panoptic segmentation is the unification of semantic and instant segmentation and object detection, unifying those together so we can make better decisions about an image, a scene, and the object within that scene. Looking at the performance requirements for such type of technology, single core object detect, object tracking for that ResNet, FAST, or CNN. Single core, likely one teraops. Multi-core, multi-object, moving to 10 teraops. Again, something that many of the embedded vision processors in the market today can support. But then an order of magnitude, a significant order of magnitude, where you're looking at that sensor fusion cluster of multi-cores up to the hundreds of teraops to manage that level of processing. Let's be clear, performance is extremely important, but it is not enough. Layered on top of that performance are the safety considerations, redundant sensor channels that, while that processing engine is managing all of that data and making decisions, that it is actually making the correct decisions. Prototypes. Prototypes are important. Today, the technology world is pretty much full of prototypes around autonomous vehicle. We see them, all over the Bay Area when we go for a drive down the 237. But another key challenge in the pursuit of semi-autonomous driving is the need to build designs where the failure rate in time is at a low enough level to allow millions of those prototypes, millions of those cars that are in production, operate without failure across the lifetime, a reasonable length of time that does not require significantly more investment on the maintenance side from the OEMs, from the car manufacturers. So how do we do that? Well, we do that through safety, understanding what it means to have a safety culture from a development perspective, understanding what it means to have a safety architecture built into our processors, built into our SoCs. We need that foundation in safety, and really that foundation in safety is made up of three important roots, basically. Systematic faults. Systematic faults, which are faults that can occur in the system, in development. They are basically bugs introduced by us as engineers in the development cycle that were not caught before the product went to release, the SoC or the processor. All of which can be found through improved methodologies or even existing methodologies that we have, state-of-the-art methodologies that we have around SoC development. Other faults that can occur, specifically in hardware, permanent hardware faults. These are hardware faults that will occur during the lifetime of the product, and these are faults that stays until removed or repaired. Again, your silicon sitting in an automobile running at 125 degrees Celsius, quite likely, next to the powertrain, needs to have a lifetime of 10 years. Faults occurs, those faults needs to be detected. Other types of faults that can occur are transient faults. These can occur in memory and in logic, more environmentally caused through alpha radiation, but a simple bit flip on a decode logic in a processor can completely change the error or the instruction execution of a particular application. Hence, extremely important for us to detect from a safety perspective. So, ISO 26262, I'm sure many of you are already familiar with this. How does it translate into the standard? So 26262 describes what's called the Automotive Safety Integrity Level, ASIL, which is broken down into three main parts. The probability of exposure, how often it is that the event will likely occur in a typical drive, the controllability by the driver, and the severity of the failure. And then you've got the different categorizations here on the left-hand side, and over on the right, you've got the resulting ASIL level. You'll hear ASIL B, ASIL C, ASIL D, where ASIL D is the highest level of safety. So as our designs, our ADAS designs, move more towards controlling more of the vehicle, active lane assist, for example, the more the responsibility goes to the technology. The more responsibility goes to the technology, the higher level of safety. So where previously designs in the ADAS market would have been ASIL B, radar or front view cameras, we're beginning to see, most definitely through our discussions with partners, etc., are moving very much more towards ASIL C and even ASIL D in some regards, which pretty much makes sense as the world moves to semi-autonomous vehicles. More safety required while also maintaining that performance capability. So, introducing you to, before we go into our SoC architecture overview, and if you're not already familiar, I want to introduce you to some of the functional safety processors that we have developed within Synopsys over the years, based on many years of experience on embedded processor development, based on many years of experience in safety development. So leveraging on that best-in-class embedded processor architectures, present the functional safety class of processors. Here, the intent is a standardization of the safety concepts and architecture through to implementation, verification, and documentation. And it's really through this standardization of safety architecture that we can reduce our customers' time to integration and final SOC certification, which is extremely important for our customers who themselves have limited resources when it comes to safety analysis and safety sign-off as they move into certification. The more we can provide that's common to them, where there's always going to be more than one, more like 8 or 10 processors on an ADAS SoC, the more standardization of those safety features and mechanisms that we can provide within that SoC, the easier it is for our customers to achieve their SoC certification. So let's jump into the SoC architecture. The modules are the cores in purple are the cores that execute the application of, in this particular case, it's a pretty generic ADAS SoC. You've got your standard VDSP cores executing radar type functionality. You've got the LPDDR, the Ethernet, pushing data in and out of system memory. All of the requirements that you need for the application. Then layered on top of that standard SoC ADAS is the safety network. And that safety network is made up of a safety manager on the top left-hand side, communicating with, in an independent mode, a safety bus. Two purposes to this. The safety manager is responsible for the boot time bring up of itself, as well as all of the other modules that are considered safety relevant on the chip to determine that no stuck-at faults are present. So it's running the memory BIST, it's running the logic BIST, reusing, utilizing the manufacturer for test infrastructure, which is this SMS SHS server infrastructure on the design, but through software to confirm that the chip is in good enough state before it moves to mission mode. So in that sense, the safety manager is responsible for the bring up. And then in mission mode, it takes responsibility for monitoring and managing any system failures, safety events that are going to occur or could occur while in mission mode. The star memory and hierarchy system interacts with the safety manager at boot time and in mission mode to run those diagnostic tests at various points in time, whether it's at the key on and key off, or indeed in mission mode for some safety critical components. So on that, in that previous block diagram, we had the safety manager. And as sure as day follows night in the semiconductor world, discrete chips begin to integrate into the larger chips in SoC. We've seen it in mobile. Automotive is no different. So the discrete MCU that previously sat in the system independently is slowly getting integrated into the larger SoCs, where that safety manager is responsible, as previously stated, for the management of all safety functions of the SoC, but providing significant ease of integration, ease even of certification, both from a hardware perspective as well as a software perspective, for our customers to get to their certification. From a software programmability perspective, if I'm programming one chip versus two, it's a heck of a lot easier to balance the API interactions and software interactions at the chip level. So a quick look at what a safety manager is. Safety manager by default is almost always ASIL-D design. ASIL-D as a safety element out of context for a processor implies it's a lockstep design. A lockstep design, in this particular case, it's our EM processor, but can also be our HS46FS processor. here, it's a lockstep of the processor and the memories, where the memories themselves have ECC protection. I want to correct that and say that the memories are not lockstep. The memories have ECC protection, which itself gives them that 99.9% diagnostic coverage through the coverage of the address and the memories. The cores, the logics are lockstep. And indeed, with the configurability of the ARC FS cores, we can include quite a number of functionalities and features: floating point, fully integrated; crypto pack engines, fully integrated; micro DMA integrated and running in lockstep, all part of that certification documentation sign-off that delivers an ASIL-D core or an ASIL-D subsystem to our customers. Layered on top of that safety manager, we have the ARC FUSA stack. This is the FUSA stack that manages through software a lot of the boot time bring up areas, processes that I described in previous slides, such as the fault management service and the test manager server, that safety boot management, as well as in mission mode, the scheduling of certain diagnostic runs, logic-based runs in mission mode that are critical to the SOC. Also would include safety watchdog manager that interacts with the various cores to determine if a fault occurs. And if a fault occurs, it's then able to look to see what is the prioritization of that fault in the system, make a determination as to whether it's a subsystem reset or if it's a simple flush of a cache that's recommended for a particular memory, or it's an entire reset of the chip, in which case that red light would go on in the dashboard. All supported within the AUTOSAR OS, and indeed other flavors of OS are also supported, SafeRTOS being a good example of that from Wittenstein. And then from an SOC perspective, we have the safety manager software. We also have the safety client software that's executing on any of the ARC processors, such as a HS application processor or an EV embedded vision processor, where they themselves can manage some of the safety activities, safety management, before they need to escalate to the safety manager. And it's through that interaction between the safety manager and the client that allows that cohesive management of the of safety within the SOC. So this takes us back to where we are today with respect to functional safety 26262. Find faults through development errors, find faults through lifetime of the product errors, find faults through environmental errors. But what about malicious type faults? We've seen, various tests and engagements that have been carried out on vehicles like the Jeep in recent years, where hackers can go in and create malicious faults within the design. So not only are we securing from the environment and securing from our own bugs, but we also need to be securing our SOCs from malicious attacks. A lot of that is actually covered in the standard, the 21434. And indeed, that is a standard that's under development. From our perspective in Synopsys, we already understand security, we understand safety. The bringing together of both of those elements is pretty much fundamental and key to a safe and secure SOC architecture. So from that perspective, coupled with the safety manager, you're going to have a T-Root HSM, secure management system, operating as a trusted execution environment and preparing the SOC or creating a trusted execution environment for the SOC. Tasks completed or owned by the T-Root HSM in this regard would be the secure boot, secure debug, key management and cryptography, authentication of the bootloader. Some bootloaders live on the system and don't need that authentication, but for some over-the-air software transactions or bootloaders that are coming externally from an outside memory, that authentication is required before code is executed on the safety manager or code is executed on the host processor. So all of these functions from a safety perspective and a security perspective is really what helps build and create that safe and secure architecture in readiness for tomorrow's next generation of ADAS designs. So maybe in closing, yes, humans are bad drivers. Why are we putting all of our effort into semi-autonomous, autonomous vehicles to improve, to make up, I guess, for bad drivers? And the role of technology is increasing to improve our driver experience and to reduce those yearly fatalities. As engineers, that's what we're striving for. That in the middle, level 2, level 3, of course, and maybe eventually level 4, level 5 fully autonomous vehicles will come. But if we concentrate our efforts in solving these key problems, we've come a long way in where we need to get to on that road to autonomous vehicles. So it's really through that combination of highest performing processors combined with a state-of-the-art safety and security architecture, combined with state-of-the-art safety concepts and methodologies, can we really meet the consumer expectations for autonomous driving, and maybe start with semi-autonomous driving, make strides towards that, onwards towards the path of autonomous vehicles somewhere in the future. Thank you for your time. Hope you enjoyed that presentation. I'll open it up now for some questions. Let me see what questions we might have. Okay, so here's one question. If you had a choice between performance and safety, which is the most important? Okay. Quite honestly, I think the answer to this question is both are important. If performance is a KPI, a key performance indicator to deliver to the use case of your ADAS design, such as the object detection or the sensor fusion, then performance is actually absolutely key. If the ability to deliver ASIL D level capabilities to that performance, then safety is the key. And we see this quite a lot where our certification houses, they always need to deliver to the highest level of safety, and that's how they audit. They are not necessarily interested in whether we as product developers have achieved our KPIs, our performance. It's the combination of both that builds the product. Only one without the other is not a product. And that, I think, is important. It's how you define what those KPIs are, and then how you demonstrate that you have achieved those KPIs. Only then do you have a viable product in the market. Okay, hopefully that answers that question. Okay, let's see if there are other questions. Do you ever see a case where ASIL D is required for neural networks? That's a good question. And neural networks, I think, is a combination of hardware and software. It's the system, and only the system is what solves the function of a neural network engine. So if the question is, does the neural network IP ever need to be ASIL D, then of course I will say the answer is yes. The answer is yes, because if a fault occurs in that processing engine and that changes a fundamental decision of that neural network engine, then it is seen as critical. How the neural network engine utilizes the information to make a decision, that's more at the system level. It's either at the SoC level, SoC vendor, or the tier one decision as to whether the operation of that neural network engine and the decisions that it's making is seen as safety critical. So from our IP perspective, as a safety element out of context, we do see cases where ASIL D is needed for the logic for those cases, because we are building our IP as a safety element out of context. We cannot ever assume the use cases of our EVs or our neural networks, in which case we develop to the highest level of safety and to the required performance level for our ASIL. So I think I'm just about over time. So unfortunately, that's all the questions I have time for today. Hopefully you enjoyed that session, and look forward to seeing you all guys in the future. Thank you.